Hello everyone, welcome to another physical sciences lesson. Our topic, we're investigating electromagnetism. Today we're going to be looking at a different slant to this topic, and we're going to be looking at what is electromagnetic induction. It might be sounding quite complicated, but actually it's very interesting and it's very useful too. So let's have a look at it. So electromagnetic induction is the topic that we're looking at, and we recognize it's got a component of electric current. That's what we would like to get out at the end, but it builds on the process of magnetism and how these two are linked. Now remember, previously we have linked these two together by saying where there is an electric current, we can produce a magnetic field. Now we're going to be looking at the opposite process, or the converse process. Can we use magnets to create electricity? And that's the first question that I want you to think about. So how can you generate a potential difference across the ends of a conductor without using a battery? Now, I've already given it away, in a sense, because we'd recognize that to do this, we don't need a battery all the time, but maybe we can use a magnet as well. And maybe you've seen those sort of torches that have got magnets in them that you shake and you can get them. Well, that's exactly the principle that we're looking at here. If you look at a bicycle as well, you turn the wheel and you'll find that the light on the bicycle goes on. It's the same principle. But let's dive into it and let's see what it's all about. And to start with, we're going to be revising some key terminology. So the terminology that I want us to look at today is the word potential difference and the word EMF. These two terms are very similar to each other, but they're very important in this context. And so I want us to look at potential difference. When we've been dealing with electric circuits, we know that potential difference is defined as the work done per unit charge between 2 points in a conductor or a circuit. The symbol for potential difference is V. It's measured, the SI units are volts, and the symbol for the word volt is also V, and the equation is V is equal to W, the work done, divided by Q, the charge. And so what you need to recognize is when we're dealing with potential difference, it's really the source of electrical energy that we've got to make a circuit work. Because remember, in a circuit, the requirement for a circuit for charge to move is we need a potential difference, we need a complete circuit that is closed, and we need that closed circuit to be made by conducting wires. So those three requirements are what allows us to use electricity and to measure it in an electric circuit. Now, that's not the only way that we can work out potential difference. We can also use Ohm's Law. Now remember, Ohm's Law is the way that we relate potential difference, current, and resistance to each other. And the equation that we've got to work out potential difference is simply this one, where we say V is equal to I times R. I sometimes forget it and I get all confused. It's on the data sheet in a different form, but I remember it because it spells a word in Afrikaans, the word vir. And so if you've ever done any Afrikaans, it might be a memory trick for you to remember the word potential difference is V is equal to I times R. It spells the word vir. Right. Now, how do we measure potential difference? This is really important because it's all very well knowing the terms, but we want to actually measure it. And there are different instruments that we use to measure potential difference. And the list is this. It's something called a voltmeter. A new instrument that we're going to come across is called the galvanometer. And the difference between the voltmeter and the galvanometer is simply where you put the zero. So on a galvanometer, you can have a negative part and a positive part, and the needle can go to the negative part. The zero is in the middle, but it could also go to the positive part over there. That's in the galvanometer. And of course, there's the multimeter. Multimeter is a digital device, but we can do exactly the same. Now, when we're looking at a voltmeter or a multimeter, remember, whatever the instrument is, we always connect to measure potential difference. The connection is in parallel. So we must make sure our connection is in parallel. Now, just to make sure that we've got this all sorted out, here's a circuit diagram with a battery in it, a voltmeter, and it's measuring in the closed circuit a potential difference. I want to just quickly look at the simulation, and let's see if we can get it up. Right, on the simulation, we recognize the voltmeter is reading 1,0 volts. The EMF of the battery is 1.5 volts, which is the same as what we've had before. What I want you to see is if we change the battery around, and now we make the positive terminal on the left-hand side, we'll see that the voltmeter, the multimeter here, is reading negative 1.50. So in this case, the current direction is in the opposite direction to which the voltmeter is expecting. The voltmeter is expecting the black terminal to be the closest to the positive side and the red to be closest to the negative, and it's in the wrong direction. If I switch the cell again, now you'll see from the positive terminal, it's coming from the positive and away at the negative, and so it's reading a positive value. And so reading potential difference is really quite important. We recognize that the terminals of the voltmeter or the multimeter or even the galvanometer are important because it could be a positive or a negative. It just tells us something about the expected direction of conventional current. Right, I think we've more or less laid the foundation for this section. There's just one last thing that I want to mention, and that is this idea of EMF. EMF is the maximum. EMF is the maximum potential difference that a battery or an energy source can supply to a circuit. And we're going to need to make sure that we are working with EMF as much as possible. And we're going to get used to doing that as we look at this principle of electromagnetic induction. So take a short break, and we'll be back to explore this in a little bit more detail. Welcome back. We're going to dive straight into finding out more about electromagnetic induction. But just to make sure that we've tied all the loose ends together, let's just revise a very important term from electromagnetism. And that term is magnetic flux. It is a kind of a difficult word to describe or term to describe, but it is very important. So it helps us link the idea together of what's happening in terms of the magnetic field. So remember, we've got a magnetic field which we can represent as B. This is the magnetic field strength. And so when we look at this, the way we represent B is by field lines. So around a bar magnet, for example, you would recognize you have a north end and a south end, and you've got these field lines that are going to run out of the north and in at the south, and they're going to form this butterfly pattern that we like to refer to. And we've even got some field lines that run out at that side, and they're going to run in at this side, and we've got this big loop of field lines. Now, those field lines are related to the magnetic field strength. We recognize where the field lines are close together. So in this area here, we've got the field lines nice and close together, and we'd say that's where the field lines are strong. Over here, there's just one field line, it's weak. Bear in mind now that magnetic flux is not just the field, but magnetic flux is defined as B times the area that is at 90 degrees to the field lines. So it's the area that the field lines cut through. So at that point, the field lines are all passing through this area. And we'd have to look at how closely those lines are packed together to get an idea of magnetic flux. If that field line is not at 90 degrees, then we introduce a mathematical term which we say is cos theta, which will help us work out what is the component of the area as if it was at 90 degrees. And so when we're working out magnetic flux, remember the symbol for magnetic flux is phi, and we're going to say phi is equal to B times A times cos theta. And in this case, in our case that we're going to look at today, we're going to be looking at the area that's at 90 degrees to the field lines. And you'll see that that's not particularly difficult to imagine and to see, and we're going to be applying that knowledge to a particular situation. So we've covered magnetic flux, and we've got a good idea now. Just to remind us in terms of how we get magnetic flux. And we've used the example of a magnet, a bar magnet, but it doesn't have to be a bar magnet. It could be a conductor that has got charges that are moving in it. In other words, a conductor that has a potential difference across the ends, and there are free moving charges, or a current that is passing through that conductor. And we've shown in previous lessons that moving charge, or a current, is going to be able to produce magnetic flux in an area around the conductor. Now, that conductor could be a straight conductor, or it could be a coil, but around it, there is this area that the field lines pass through it. And we've used the crosses and dots to represent that magnetic flux, or those magnetic field lines, and we've been able to say where they're close together, high magnetic flux, where they're further apart, low magnetic flux. I hope you remember that. Now, this was the state of affairs in the middle of the sort of 1800s. The kind of people had been playing, Ørsted has been playing with working out magnetic fields around a conductor. And this physicist from one of the Scandinavian countries, it was a breakthrough to be able to see that there was a relationship between electricity and magnetism. But the key idea was, is there a way to use magnets to create electricity? Because again, at this stage, they only had very primitive cells, batteries, electrochemical cells. And they weren't very reliable. So people wanted to have electricity, and the idea was, let's use magnets to make electricity. And the man that came to the rescue was a really important physicist. He came from a very poor background. His name is Michael Faraday. He wasn't even supposed to be a scientist, but he worked out that if we take magnets and we allow the magnetic flux to change, and we allow the magnetic flux by either changing the position of a coil, so you can move a coil, or you can move a magnet. If you move either of these, then guess what happens? You induce an EMF. If the coil is just a coil that isn't connected in a closed circuit, it will produce an EMF across the ends. But if we connect it into a loop, into a closed circuit, then we will get a current induced as well. And we would say, if there's a current induced, then we've got moving charge. So this is converse thinking. Initially, we said moving charges produces magnetic field. Now we're saying, let's change the magnetic flux, move the magnets or move the coil in the magnetic field, around the magnetic field, and what do we get? We get an induced EMF, a moving charge, if it's a closed circuit. And that's really important for us. So let's just go and explore this. Now, we can't do it in detail, but we have a simulation. So let's go and have a look at the simulation. Here's my magnet. And what I want you to see, I've made it really simple. I've connected this coil to a light bulb, and I'm simply going to move the magnet in and out of the coil. And what do you notice is as I do that, the light bulb goes on and off. Now, if I turn the magnet around, it doesn't make any difference. It still goes in and out and making the light bulb shine. Now, you might say to me, what happens if I do it above and I don't do it in the coil? Well, the light bulb still goes on and off, but not to the same degree, because it is better if it goes through the middle of the coil. Okay, so that's quite interesting. We can also just do a little experiment here, is if I put it through a smaller coil and try and move it more or less at the same speed, you'll see it's going, the light bulb's going on and off. But through the bigger coil, it looks to me like the light bulb is burning brighter, or is indicated to be burning brighter. So as we do this sort of experiment, there's lots of observations and things that we can start to look at. The ways of trying to explain what's actually happening. So let's go to summarize some of what we've seen. And the first thing that I wanted us to look at is to say, well, what are the factors that affect the induced EMF in a coil? Now, at this stage, I'm just using the light bulb, the shining light bulb, as an indication of how strong the EMF is. If the EMF is very big, then the light bulb will shine brightly. We know that's the case. If you have a 9-volt battery and you have a 1.5-volt battery, the 9-volt battery is going to give you a much brighter light bulb. And so we're not making things up here. We recognize that the induced EMF is going to be bigger if you've got a bigger number of turns in the coil. You've just seen that. But are there any other factors that we might consider? Now, this next one, we're going to need to go and have another look at the simulation, and we're going to have to look at how the magnetic flux changes in the coil. So the change of magnetic flux in the coil. And this is something that Michael Faraday took a long time to come to explain and realize, and it's part of the statement of what we now know as Faraday's Law. So let's go and have a look at this and adapt our simulation a little bit. I'm going to put in some field lines, and I'm also going to put in a voltmeter. So I'm going to revert to just one coil, and at the moment, I'm going to change it around as well, just to have the North Pole over here. So as you can see, the field lines close to the North Pole, there are lots of them. They're close together. So what do we know? That's lots of magnetic flux. Now, if you compare the amount of flux that is going through the coil in that position, what would you say about the amount of magnetic flux? Well, I think you can see it's hardly anything. But if we bring the magnet closer to the coil, push the magnet into the coil, then the amount of field lines cutting through that area in the coil, that magnetic flux is going to increase. And even the ones that are cutting past the wires of the coil, they will increase here. So these curved ones cutting through the wires, they're increasing. So if I move this, you recognize this is a low position of flux. And if I move it to that position, you'll see that there is more flux through the coil at that point. But what do you notice at the moment as I've changed those positions, the reading on the voltmeter and the light bulb aren't glowing. It doesn't look like there's much happening here. So yes, the flux has changed, but there doesn't seem an impact. That's because of the next idea, and that is that it's all dependent on the change in magnetic flux. Because at the moment, is that magnetic flux changing? No, it's the same as it was a second before. It's not changed. But watch here. From that position, low magnetic flux, watch what happens to the needle as I do this. High magnetic flux. Now I've stopped. But in that point between low and high, there was a change in magnetic flux. You know, if your marks start off at the beginning of the year and they're particularly low, and they, over the progression of time, they increase, that's a big change in your marks. And that's exactly what's happening here. There's a change with respect to the magnetic flux, but also with respect to time. But now it's staying stationary because there's no change. So only when there's a change in magnetic flux, and that's the important thing. Either the coil has to be moving or the magnet has to be moving for us to appreciate a change. And I hope you've got that idea. So if you take a careful look, and you look carefully here, if I do this, you'll see I'm changing it continually. And the light bulb is flickering on and off. So as long as there's a change in magnetic flux, there's going to be an induced EMF. Now, the last thing that I want to just say very carefully here is it's not just about the change in magnetic flux. It's also about the rate of change. And when we talk about the rate of change, we're talking about a measure of time. It's about how quickly or slowly the change takes place. So have a look here. I'm going to deliberately move this magnet into the field very slowly and out very slowly and back again very slowly. And you'll see there was hardly any movement of that needle. Now what I'm going to do is I'm going to move it quickly as I can. And you can see that it's jumping backwards and forwards in a much bigger way if I move it just backwards and forwards over here. Because there's a bigger change, or the rate of change of magnetic flux is bigger. And so that helps us to understand the factors that affect our induced EMF. And so we've looked at the change. Remember, there has to be a change in the speed of the motion gives us the idea of the rate of change. And so here, let's put it all together. Faradays Law says the EMF induced in a coil is directly proportional to the rate of change of magnetic flux. And we use this equation. E is equal to the number of turns. There's a negative sign outside. The change in magnetic flux divided by the change in time. And we've said the flux is the field strength times area times cos theta. Don't go away. We'll be right back. Take a short break, and we'll see you soon. Hello everyone, we're doing a physical science lesson today, and we're investigating some more detail about electromagnetic induction. Now, it's a fascinating topic, and we are really grateful to Michael Faraday, who discovered this very important principle. Because you know what, if it wasn't for Michael Faraday, then electricity and magnetism would be lost. And it would just be a theory in a dusty old book that sits in a library. But when we think about all the things that we've got, all the tools that we've got, the reason that things work is because of our understanding of this principle of electromagnetic induction. Because without being able to produce electricity in a reasonably cheap and easy way, we would never be able to explore it and have all these devices that we depend on. And it gets even better, because even as far as your cell phone, the charging of your cell phone, you need the principle of electromagnetic induction. How about that? So it's a very important principle. So in trying to understand it, I know that you probably have seen how a magnet moves into a coil. But to really understand it, I need to remind you about this important rule, the right-hand solenoid rule. Now, remember, I'm left-handed, so I can put my hand away, and I've got my right hand now available to be able to indicate the direction of the current, which I use my fingers for. So in a coil, there are many fingers, so I'm going to use the many fingers for the direction of the current, and there's one thumb that's going to point to the one north pole. So the thumb gives you the north pole, and the fingers gives you the direction of the current. We're going to need to be very careful to be able to use it both ways, to both be able to say, well, if the north pole is here, what's the direction of the current? And if the current is going in this direction, what's the direction of the north pole? And those are two interrelated ideas. Remember that the right-hand solenoid rule is just a method for us to use to find the north pole of a loop or a coil, and we've done this in previous lessons. So I hope you've been practicing and you can use the right-hand solenoid rule. So why is this important? Well, it's important because it helps us understand that when we're moving the magnet into the coil, what's happening inside the coil. And in effect, we're saying, let's investigate the direction of the EMF. Let's investigate the direction of the current, because it's a closed circuit. And how can we predict what's going to happen? So here's an important idea that I want to share with you. It was discovered by observation by a man called Lenz. And he came up with this idea that if you push a north pole into a coil, then the coil itself tries to repel the approaching north pole. And if you try and take away the north pole, you pull the north pole out, then the coil becomes a south pole end because it rejects the change. It doesn't want to change it. Now, to help us remember, I call it the undecided teenager rule. And you know what that means. You might think that you like somebody very much and you want to get close to them. And as you approach, they say, no, go away, we don't want you. And as you go away, as you start to leave and say, oh, well, that's that one. I'm never going to have a relationship with him or her. Then they say, no, come back. And as you come back, they say, no, go away. As you find that you want to then leave, no, come back, I've changed my mind. So this is known as Lenz's law, but it's nice to remember it as the undecided teenager. So how can we predict and how can we work out what is exactly happening? So I'm going to use the right-hand rule. Let's imagine for a moment that we've got this magnet moving in to that coil. So what does Lenz's law tell us? And what is the principle that we're looking at here? It says that this coil that I'm putting over there, a block around, it becomes a magnet because inside or across its ends, there's an induced EMF. And if there's an induced EMF, there's the potential for current to flow, and in fact, there is a closed circuit, so current will flow. And if current flows in a coil, what happens? It becomes an electromagnet. It becomes a solenoid. And the solenoid must have a north pole. It must have a south pole. Which direction? How are we going to know? Well, according to Lenz's law, if the approaching magnet is a north pole, then this end here must be a north pole, and this end must be a south pole. So now let's apply the right-hand solenoid rule. And we're going to say, well, I want that end to be a north pole. Well, then that means that according to Lenz's law, then if that's the north pole, the thumb points to the north pole, it's my right hand, then the current must go down and around like that. So on this diagram, I'm going to say it's going down and around like that. And that means that it's going to go up on that side, it's going to go in that direction, and it means that it's going to come in on this side, and it's going to come around like that. And so on my diagram, I can indicate the direction of current. But just to make it a little bit easier, I'd like us to use the different notation for being able to show what's happening. So instead of using these field lines and this sort of notation, let's go to this scenario, where the coil now is represented by the cross-section of those wires being the little circles. We're looking at the top of them. We're going to have to decide in which direction is the current going to be induced in this completed circuit. We'll say it's a completed circuit. So again, we're going to apply Lenz's law. We say at the moment, the north pole is far away, so it's not going to be a very big induced EMF, not a very big induced current. So it's a very small EMF. But if we bring it closer together, the magnet has now moved. There's been a change in magnetic flux. And if there's a change in magnetic flux from the far away to close together, then there's an induced EMF in the coil. What's going to happen? Well, we recognize the north pole was approaching. And that tells us that this solenoid, this coil, has to produce a north pole. So if I'm going to use the right-hand solenoid rule, remember, the many fingers will tell me the direction of the current, and the thumb tells me the direction of the north pole. Now, I know what the direction of the north pole is. It's to this side, and I'm going to just turn and work over there like that. So I'm pointing my thumb towards the north pole because it wants to repel this approaching north pole. And now you'll see that the curl of my fingers is into the board. Can you remember what symbol we use or how we denote when the current is going into the board? What do we use? We're going to use a cross or a dot, but into the board means it's got to be a cross. So on each of these, I'm going to draw a cross. Now, if that's the North Pole, look over here. If that's the North Pole, then over here at the top, the fingers are coming out. And if the fingers are coming out, then I'm going to put a dot over here to show that the current is coming out of these coils like that. And so I've been able to show you that as the North Pole approaches, the direction of the current in the wires is going to be in a particular direction. Depending on the way that the wire is wound around the coil, that can also make a difference. But I hope you can see how we can annotate the direction of the current. Let's look at the other situation. What do you think will happen if we change the pole of the magnet? And so what we've got here is a south pole. And we recognize that the south pole is in that position, and now it's gone further away. So the south pole was pretty close, and it's now gone further away. What do you think is going to happen? What does Lenz's law say? Remember the undecided teenager? You're pulling the south pole away. Well, guys, this is also going to be a change in decision. Not to, this one is moving away. So what does the coil do? Say, no, please don't leave me alone. Help me, help me, help me. Come back, come back, come back. And so this has to be a north pole as well. And so we apply the right-hand solenoid rule again, and you see that it will go in on this side, and it will come out on that side, just like we had previously. So please remember that if the magnet was moving in a different direction, then the current would be passing through the coil in a different direction as well. So I hope you've got this idea and you can begin to understand that the direction of the induced EMF can be different depending on the direction that the magnet is moving in. And that's the important thing. We're going to use this information to help us predict in which direction the needle on the voltmeter is going to go. And I hope you've got all these facts together. Please make sure you take a very quick break, revise the few facts that we've dealt with, and get ready so that we can apply this idea of Faraday's law and Lenz's law in our next segment. So we'll see you after the break. Welcome back, everyone. We're going to apply all that we've learned so far about electromagnetic induction in this particular example. We're going to try and predict what direction the needle on the voltmeter is going as we place and we move a magnet into a coil. Now remember, you could be moving the coil inside a fixed magnet. That's fine. They've just got to move relative to each other. But for the moment, let's just use this example. So to remind ourselves a little bit, let's first of all go back to a normal circuit. And we looked at this earlier. We recognized conventional current is from the positive end of a battery to the negative end. So the direction of the current would be around in this direction. And what we're seeing here is this is the positive terminal of the voltmeter, and this is the negative terminal of the voltmeter. You can see where the current is coming in is closest to the positive terminal, and where the current is leaving, it's closest to the negative terminal. The direction of the current across this resistor is from the red to the black. And that's why this is a positive reading here. And that's how we must make sure that we can predict in which way the voltmeter is going to read. Is the current going in at the terminal that is marked positive, or is it going in at the terminal that is marked negative? If it goes in at the terminal marked positive on the voltmeter, it will give a positive reading. If it goes in at the terminal marked negative, it will give a negative reading. So it's very important that we put all the little pieces together so we can make our prediction. And so here we go. Here is our scenario, and we're going to first of all think about it and work through it and see if we can make a prediction. Then we'll go and look at the simulation and see if our simulation is correct. So in this example, let's say that the magnet is moving into the coil in that direction. We've already established when that happens that this end must be a north pole as well. And then using the right-hand solenoid rule, we recognize the current must be going down on this side and all the way down, and if you follow this line, it will go up on that side, it will go in that direction, which means the current is going in at the negative, and it's going to be coming out at the positive all the way around to here, and in the background, it will go up there and it will come down, and there we've got the whole scenario. So if you use our right-hand solenoid rule, we can predict the north pole will be on that side, and we recognize that it's going in at the negative and out of the positive of the voltmeter. So what do you think that means? In which direction is that needle going to go? Is it going to head towards the positive end, or is it going to end towards the negative end? You need to make it clear in your mind, but let's go and test it. You see, this is what I love about science. We can make a prediction, and then we're going to go see if we're right, if our thinking is correct, and let's hope that we are. And here we go. We've got the North Pole over here, and we're going to move the North Pole towards this coil. Now, I haven't put the field lines on because they're sometimes a little confusing, but I'm going to move it in And what did you see? As it moved in which direction did that needle go? There, it's going towards the negative. And what did we say? We said that as we move it in, it will go towards the negative. Now, notice what else happens. As we move it in, it moved towards the negative. As we pulled it out, it went towards the positive. And that is exactly what we predicted as well. Remember, if the one end is a north pole when you move it in, if you try and take it out, it wants to pull the north pole back, and so it will swap poles. It will go to the south pole. And if it goes to the south pole, then we'll be able to see which way the current is going. The current will go in the opposite direction. In other words, it will go in at the positive and out at the negative. But let's make sure that we've got that, and we're going to have another look at it. So let's go back to our original diagram. Let's go back to our original diagram, and let's have a look at what we're going to do here. So in this scenario, what we're going to say is let's predict what will happen, and we're just going to confirm our prediction if we move the north pole in that direction. So remember what will happen. Think about it carefully. Remember, the magnetic flux is changing. Because the magnetic flux is changing, we're going to get an induced current. We're going to get an induced current because it's a closed circuit. There's going to be an EMF induced across the terminal, and that's what's causing the charges to move, the charges to flow. When we move that north pole out, remember the crazy teenager who can't make up their mind? What's going to happen? The north pole is running away. They say, come back, come back, come back. So how are they going to make the north pole come back? This end has to be a south pole, because the south pole is going to attract the north pole. The north pole, they will repel each other. The south pole here will attract. And if the south pole is attracting, what do we do with our right-hand rule? Well, we take our right hand and we say, we don't want this end to be a north pole anymore. We want this end to be the north pole, because that end has to be the south pole. And if that's the case, right-hand rule, notice now the current has to be going in the opposite direction to which it was earlier. So that means that it's coming in at that side. And that means that it must be going up over here, and it must be going along over here. And I've marked all these points. So it goes in at the positive, and it's going to come out at the negative through the light bulb. And so we've got the completed circuit. And in which direction is the needle going to go? Well, if it goes in at the positive, then we're going to predict it's going to go positive deflection in that way. And that's just what we've seen. So we've put the things together. Remember, the order that we recognize is, first of all, there's got to be a change in magnetic flux. If that magnet is just sitting there, it's going to do nothing. It's going to stay a reading on the voltmeter of 0. But if there's a change in magnetic flux, the magnet is moving in or out, or the coil is moving in or out relative to the magnet, there's going to be a change. There's going to be an EMF induced. And so what we recognize, if there's a change in magnetic flux, then we're going to say there's an EMF induced. And now we're going to say in which direction. We're going to apply Lenz's law. We're going to use the right-hand solenoid rule. Right-hand solenoid. And if you've got the right-hand solenoid rule, you can then decide in terms of the direction of the current. And the direction of the current will then help you determine the direction of the needle. So there are multi-steps there. But I hope that you can see, by looking at these step by step, one by one, you'll be able to master this whole idea. Now, we can do this over and over again, but we're not going to do that. What I'd rather do is say, so what does this mean if we've got a different representation? What does this mean if the picture looks a little bit different to what we've had before? So here's what I'm going to do. Is I'm going to say this piece of wire and this piece of wire are connected to the voltmeter over here, where this side is the positive end and this side is the negative end. Now, that's how we've set up the circuit. Now, I want us to be very clear about what we're going to do. And let's make sure that we've got this right. Let's say, in this case, we're going to move the North Pole away. Think about it. If we're moving the North Pole away, what's going to happen to the end of the coil? Well, according to Lenz's law, this end has to become a south end because it's going to oppose the motion that is being made. It tries to undo and put back where it was. So it calls the magnet back to where it was. So it's going to make that end the south pole. Now, if that's a south pole, then I need to recognize using my right-hand solenoid rule that this end must be a north pole. For that to be true, I've got to recognize that for the bottom coils here, the current is going to, see my thumb is pointing to that side, the north pole. The current is going to come out of this side. Current is coming out of this side. Current is coming out of this side. And it's going in on this side. So the current is going in on this side. And if the current goes in on this side, then we recognize that it's going to go down here and it's going to go in at the negative. And if it goes in at the negative and out at the positive, in which direction is the needle going to go? Well, we said if it goes in at the positive and out at the negative, then it will go in the positive direction. So in this case, the needle will be deflected to the negative, will go negative. Okay. So guys, there are multiple combinations of this type of question that they can ask you in a test or an exam. Please just practice. Use the simple, clear thinking that we've established and make sure that you've learned the laws. Before we go, I just want to pick up on two little points. The first one is, so what's the use of all this? Remember I said to you that this was probably the most important discovery of the 1800s. The whole set of work that was done in the 17 and 1800s actually opened up the field of physics for us and helps us to understand a whole lot, even as much as what the light is and the televisions that you're watching this on and the devices you're looking, all started because of an understanding of electromagnetic induction. And so even on this picture where we have power lines, the reason I've shown this is because power lines are indicating to us the way that electricity is taken from the power station, usually far away from the city, and then brought closer to our homes. And for that to work and for us not to lose lots of energy, you need a transformer. Now, for a transformer to work, even your cell phone little charger has a transformer in it. And for that to work, you need to have the principle of electromagnetic induction. Without electromagnetic induction, transformers wouldn't work, generators wouldn't work, and we would be much the poorer. So let's make sure that we are grateful to a great man, Michael Faraday, for discovering this principle, not just discovering it, making it clear to us, making it useful so that we can today have benefits of the work that he did. Now, final thing, summary for you. Remember, changing magnetic flux is required to induce an EMF across the ends of a coil. The induced current is directly proportional to the rate of change of magnetic flux, and we use the principle of electromagnetic induction for transformers and generators. Thank you for joining me today. I hope you've enjoyed our initial introduction to electromagnetic induction. Please join me again as we continue the story in our next lesson.